Good morning, GMGM. Thank you, everybody here, for choosing to spend your time at our third inaugural NoirCon.
Amazing. Thank you. Hello, everyone. Welcome. My name is Ciara Nightingale. I actually work for a company called Cyfrin, but at the moment I'm working with the Aztec team to help them with some technical education. So that's why I'm here. And yeah, so we're just going to do an intro to Aztec. This is going to be pretty informal, so it's more like a chat. It's going to get more interactive later in the day. So Josh is going to be doing a run through of getting your development environment set up. But before we do any of that, we need to understand what Aztec is. So what the hell is Aztec? And then also, how is it different from Ethereum? So because things have private state, which hopefully you guys know, but if you don't, no worries, then it is a little bit different from Ethereum and Ethereum compatible or Ethereum equivalent chains. So you need to know about those differences. This is pretty quirky stuff. It's a bit weird. So if you don't understand it in this session, I'm not worried at all. I kind of just want to give you familiarity with some of the concepts, some of the words, so that when you hear them, you're like, oh, I kind of know like what that sort of means. And then you can go back to the documentation, read up on it again, read around the subject. And hopefully it'll just like keep repeating, because repetition is the mother of skill. So, and I keep talking. I talk a lot is what you're going to find out. So yeah, let's get on with it. There was something else I was going to say, but I can't remember what it was. Oh, who here is a developer? Can I see a show of hands? Okay. Yay! Amazing.
That's good.
I was banking on that. So who here knows Solidity? Solidity developers? Also amazing. Thank you all for being here. And then also, if you already know all of this and you decide halfway through that like you want to go to a different room, I'm also not worried, because I've been in talks before where I'm like, oh, I feel like I should have been in a different room. If you want to leave or come in and out, like that's absolutely fine with me. So also feel free to do so. That's what I was going to say. Yeah, so the prereqs, what I'm going to assume you know, which apparently you all know anyway, which is amazing, is that you're a Solidity developer, you know what a smart contract is, you understand why blockchains are awesome, you understand a little bit about what zero-knowledge proofs are and why they're cool. I'm not really going to be going through that. And you understand what Merkle trees are and the Ethereum state model. If you don't know about the Ethereum state model, also fine, because we're going to be going through it briefly, but hopefully it'll just be like a little recap. Hopefully you all understand why Aztec is awesome. Aztec is awesome because we have programmable privacy. What is Aztec? It's all of these words. But I like to say ZK rollup because I think it sounds funny. But it's just a ZK rollup, so we're using ZK proofs for proving state changes, like normal ZK rollups. But then we're also using zero-knowledge proofs for proving private state. So I don't want Pala to be able to see my balance. I don't want you guys to be able to see my on-chain activity. So we have privacy, because blockchains are really awesome. We have transparency, which means that no one can lie. We have verifiable state, because you can literally see it. But that is at the sacrifice of privacy. And in the Web 2 world, the amazing thing about Web 2 is that we do have privacy. It's centralized privacy, which isn't great, but what if we could have a world where we have decentralized privacy, which would be flipping awesome, and that's what Aztec does. Aztec, as a top line, is a privacy-focused L2 on Ethereum. So if you take one thing away, it's that. If you don't understand anything else from the rest of this presentation, I don't really mind. It's just this. So we've got private state. So Aztec has two different types of state. Not everything on Aztec is private. That was my assumption when I started learning about Aztec. I was like, everything in the whole of everything is private. That's not the case. You have public state and you have private state. So it's up to the users and the developers to choose what state they want to be public and what state they want to be private. The public state is visible to everyone in the same way that it is normally. Everyone can just look at the blockchain and see the total supply or whatever they want. And then the private state is visible only to the person who owns that data. So let's say the simplest example is your balance. You will only be able to see your balance. You're the only person that will have access to that, unless, of course, you choose to share it with someone. Public state is a lot less complex than private state, so we're going to go through that first. It works exactly the same, well, pretty much exactly the same as it does on Ethereum. So it's account-based. It's all public functions are executed on-chain, and all public state is stored on-chain in a public state Merkle tree. So it's exactly the same. Well, it's a Merkle tree rather than a Merkle Patricia tree, so there's some small differences, but from the developer perspective, you can consider it to be exactly the same. So it's account-based. Let's say it's a balance again. You'll have some key, like your address, which will then map to some value, which is your balance. This is then stored. Did I put the slide? No. It's stored in a Merkle tree. So then when you update your balance, you'll be pointing to a specific storage slot in the Merkle tree, and it'll be updated. And everyone can see it. Everyone can see what storage slot you're accessing. The end. Private state cannot be stored on-chain, and private functions cannot be executed on-chain. Because, of course, if we did that, everyone would be able to see it. So that would not be a good thing, so we can't do this. Therefore, we've got to do things differently. So instead, we execute private functions off-chain, and we store private state off-chain in its raw form. We then prove the execution on-chain by sending a ZK proof to the sequences. That's pretty much it. Sounds not too complex, because, to be honest, at this point, it's not. Private state is off-chain, public state is on-chain. That's it. Imagine if it was that easy.
Yeah. 3 years working, and it was that easy.
Yeah, well, there you go.
Go figure.
What took all this time, huh? Right, so private state is not account-based, like public state. Why? Is because, let's imagine for a second that it is account-based. Let's say we just encrypted our key and encrypted our value. Let's say, again, it's a balance, maps to some encrypted amount. We would then store that in a Merkle tree, and then when you access that Merkle tree, let's say I'm updating my balance, even if the values are encrypted, you will leak which storage slot you're accessing. And that itself leaks information, which breaks privacy assumptions, which is not a good thing. So we definitely don't want to do this. So that is why it's a bit more complicated and it's taken more time.
Exactly.
So instead of using an account-based model, we use a UTX-based model. And who knows about UTXOs? Who knows how they work?
Huh.
Okay, pretty much everyone. So this is going to be really easy. Nice. It works exactly the same, well, pretty much exactly the same as physical cache. So rather than storing a full balance somewhere, you instead have individual notes that will add up to your balance, but you're never actually storing the full amount. And now this on Bitcoin is just balances, but for Aztec, this is going to be any data. But we're going to stick with the balance example for now because it's the simplest to think about. So let's say I had a $20 banknote, and I also have a $10 banknote. I want to pay Pala $25. I would have to give him both of my notes, my banknotes, and then Pala would have to give me 5 back. So then the value transfer is 25, and that's pretty much it. And so with private state, it works pretty much the same, except rather than it just being normal UTXOs, which are stored on-chain, it's stored off-chain in something called notes. And notes to me, when I started learning Aztec, were like so confusing. I understood it conceptually, and then I was like, okay, but like, what actually is a note? It's literally just a struct. It's just some data. The data we call a note because it has some special functions as well as this struct to be able to do some things that we're going to talk about later. But from your guys' perspective, it's literally just some private data. So these values can be anything you want. Here I've given the example of a uint note, but these can be anything. So we've got some owner, some randomness, and a value. The randomness will come into it later. I don't think the mic's working, by the way.
Yeah. Hello, 1, 2, 3.
I don't think it's working. Can you guys hear anyway? Okay, well, I'll just continue anyway and then hope for the best. Pray for my voice, please. Yeah, so it's just a private struct. And then these notes are stored off-chain. So you've just got your collection of notes which you store on your local machine. And that's it. So yeah, you've got all these notes here. But how do we track this private data? How do we make sure that everything is still verifiable? We can't store them on-chain as these raw notes, because obviously we don't want everyone to be able to see it. So instead, we create commitments. Who knows what a commitment is? So I want to see a show of hands for that. Okay, pretty much everyone. A commitment is basically just a hash, but you can't, it just protects against brute force attacks, pretty much. So we create these hashes of the notes, and then we store them in a note hash tree, which exists on chain. So no one can see what the notes are because they're hashed. And then they're stored in this tree to make sure that we can have verifiability, because people can prove that they own the notes by proving they know the pre-image to a note hash that exists in the Merkle tree. This note hash Merkle tree is append only. You can't edit in situ, you can't change a note, you can't delete notes from the, we're back. We can't delete notes from the tree. So let's say I'm paying Pala again, I've got a 10 token note and a 20 token note. I want to send him 25 tokens. I'd need to first find a way to either edit my notes or get rid of my notes and create my new 5 token note and a 25 token note. So a 25 token note for Pala and a 5 token note for myself as my remainder. But if it's append only and I can't remove notes from the tree, how do I know which ones are used? How do I know which ones have been removed, and how can I edit them? How can I remove them?
Yeah. How do you prevent double spends, basically?
Pardon?
How do you prevent a double spend?
How do you prevent a double spend? Exactly, thank you. And the way you do that is through nullifiers. So I have to create a way to delete these notes effectively and mark them in the Merkle tree as spent. I have to be like, these notes in the Merkle tree have been used and they can't be reused. And we do that using nullifiers. So let's say you have all of these notes stored locally on your machine. Some of your notes that you have used will be spent. And to mark them as spent, you will create a unique nullifier, which will be based off of the data in the note, plus the person who can spend them, to make sure that it's unique for each person. So each note that is spent will have its own nullifier. And then these nullifiers are stored on-chain in their own Merkle tree called the nullifier Merkle tree. Yay! And that, to be honest, is pretty much it. So let's go through an example. I'll have my original example. So I've got a 10 token note and a 20 token note. I want to send Pala 25 tokens. So I first need to first I need to prove that I know the pre-image to 2 commitments in the Merkle tree. So I prove that I have ownership of these 2 notes, the 20 token note and the 10 token note. I then need to nullify both of these notes. I need to mark them as spent. I need to destroy them. And I can't remove them from the tree, so I create 2 nullifiers and I add them to the nullifier Merkle tree. So these two notes are now used. I then create 2 new notes, one 25 token note, which I give to Pala, and one 5 token note, which I keep. How do I share my 25 token note with Pala? A little bit complicated. I could share it off-chain. I could send an email. I could create a QR code, which he could scan. I could send it via carrier pigeon, but I could also use note discovery, which is a little bit more complex. Maybe, Pala, you could give a little bit of a spiel on note discovery. I haven't prepped him on this, so...
No, not at all. And I know it has changed yesterday, literally.
Oh.
I'm not kidding. Yes.
Of course.
Sorry, there was a question?
Oh, sorry.
Yeah.
How are the nullifiers computed in such a way that they don't reveal the information about the node?
Yeah. Do you want to take it?
Yeah, you go for it.
Okay. So nullifier is a hash, right? Same as the commitment. It's a different hash altogether. And the thing with nullifiers is they need to be deterministic. Like, you need to be sure that whenever you have a node and you produce its nullifier, it's always going to be the same. Otherwise, you could produce different nullifiers and spend your node multiple times. So what we do is we take part of your private key, if you will, is shuffled into that hash that we use for producing the nullifier. That way, the nullifier is a commitment to the node, and it's something that only you as the owner can produce and no one else. Because otherwise, let's go back to the example where she had sent me a node for $25. Then whenever I nullify that node, if I didn't include anything secret in there, she would know when I spent the node she gave me. And we don't want that. So we mix some secret thingies into that commitment. Here? OK.
OK, amazing.
Yeah, sorry.
Okay.
Just speak very loud.
Yeah, just speak up.
Some question about the private state and public state.
Yeah.
Which one?
Oh, just that the private state is stored privately, it's not on chain, right? So I suppose it is somewhere like in the client wallet.
In the what, sorry?
Test.
The private state?
Yes.
Because it's storing privately, so I assume it's storing in the client wallet.
Yes.
Something like that.
Yep.
And if I somehow like screw up my computer and format it, and how do I is it possible to restore my private states?
Yes.
Given it's only the commitment that I store.
We call that the throw your laptop in the ocean test. Not kidding. We've been using that term for a long time. And it's going to depend on two things, on your wallet and the application you're interacting with. As Ciara was mentioning, you could architect your smart contracts, like your applications, so that whenever a note is sent, it's actually broadcasted on chain, encrypted. So only you can find and discover it and actually understand what it means. And that ultimately, since we're a rollup, that goes into Ethereum blocks. Like it gets stored somewhere that you can retrieve later. What's the downside with that? It's expensive. You're paying for blob space. So it's up to the application you're interacting with to decide whether every single node, every single piece of private data wants to be emitted on-chain, encrypted, or not. So that's an application decision. Then you have a wallet decision, which is how am I going to back up all my client data? So for all of those nodes that were not emitted encrypted on-chain, how am I storing them? And yes, one option is store them locally and pray that your laptop doesn't fall into the ocean, which is definitely not the best option. So most wallet teams that we're working on are looking into some backup solutions, like they encrypt your private state and back up to cloud provider or whatever it is, or multi-device or anything else. But yes, it's a very good point. If you haven't emitted those nodes on-chain encrypted, you need to make sure that the wallet the client is using, the end user is using, has some sort of backup. Otherwise, you lose access to your stuff.
Thank you.
Sure. I'm sorry, I think like what this goes into, is that a wallet in Aztec is a much bigger beast than it is in Ethereum. It's not just something that signs. It's something that needs to execute code locally, that needs to generate proofs, that needs to keep local state, and also needs to have your own keys.
Thank you, Paolo.
Anytime.
Very good answer. I've just created a little slide about when to use private functions. Actually, this is stolen from Josh, so thanks, Josh. So basically any time that you're working with private state, you'll want a private function. If you want sensitive data that you don't want stored on chain, of course. If you want to hide any function execution. If you want to create a proof against historic data, so there's an archive Merkle tree in there's 5 Merkle trees, by the way, in Aztec. I'm going to try and do this off the top of my head, so hope for the best for me. Public state Merkle tree. We've got the note hash Merkle tree. We've got the nullifier Merkle tree. We have the archive Merkle tree, and then we have the L1 to L2 messaging Merkle tree. Sorry, just testing myself there. And yeah, so proving against historic data, and then let's say you wanted to move some state from public to private. I don't know. What's an example of when you'd want to move it from public to private? Can you think of
Shielding
one?
your assets.
Okay, fine. Yeah, shielding your assets. Great example. Thank you.
Anytime.
When would you want to use a public function? Pretty much the same as you would normally. So yeah, anytime you need some shared state, maybe it was like a total supply or some health factor that you need to, like the minimum health factor. Interacting with current head of state, using the block data, block timestamp, that sort of thing. If you want information to be available to everyone, of course you need it to be public so that everyone can see it. Taking data from private to public. And then also anything which you want to reveal at a later date. Let's say, it's like a card game and you want to reveal the cards at the end of the game. You'd need to use a public function to be able to do that. And then there's a slide which I have stolen again from Josh. Thanks, Josh. On the transaction lifecycle. I think, Paolo, it would be really helpful if you could go through the transaction lifecycle. Feel free to use the slide or just spitball if you want.
Yeah, absolutely. So the idea is, let's start with the separation of the different tranches here that involve the transaction lifecycle. First, the separation between purple and yellow, right? Like purple, which is everything that happens in private land, is what happens in the user device. And it happens when the user is sending the transaction. They specify what they want to do, they execute, they generate the proof, etc., etc. That all happens at one moment in time. It happens when the user is creating a transaction on their device. That transaction gets sent to a node, and eventually, as in Ethereum, it gets picked up by a sequencer and included in a block. When that happens, the public side of the transaction is executed. Remember, transactions can involve private functions and public functions. And you can have private and public functions in the same contract operating in tandem with one another. Like you could do something in private to prove you have some assets and generate a side effect based on that on public. Or you could check a condition in public that you couldn't check in private. For instance, you could allow people to participate in an event up until that event gets filled. So you can handle the participation in private, but you do the check on, hey, has the event completed or not in public? Why? Because public happens when the transaction is actually mined, gets actually included in the block, same as in Ethereum. So that tandem between private and public lets you do as much as you can locally on the client without revealing anything, and only rely on public when you need either interacting with other things, like Ciara was mentioning, or validating that you are in a good moment for the transaction to happen, right? Things that are time dependent or inclusion dependent or dependent in the global state. So what's the overall life cycle? Like the user is going to accept from the wallet sending a particular transaction, same as in Ethereum. And then the wallet is going to work with a local component that we call the Pixie, Private Execution Environment, which is a client-side library that we built at Aztec. Wallets are developed by external teams, and we expect to have a lot of wallet diversity. But all wallets are going to rely on this small component that, again, runs client-side and is in charge of actually executing all the private functions involved. Not just executing, but also generating a zero-knowledge proof. The Pixie is going to have a couple of callbacks to the wallet, like the Pixie is going to ask the wallet, for instance, to provide the nodes that the user is holding. Like in the example where Ciara is sending me money, what's going to happen is the user is going to tell the wallet that they want to initiate a transfer. The wallet is going to call into the Pixie saying, I want to call the transfer function, the private transfer function of this particular token. The Pixie will start execution. At some point, the token contract logic will say, okay, give me nodes to get up to 25 tokens. That's responsibility of the wallet and how the wallet is persisting state to provide those nodes back into the Pixie, which will keep executing. Contract logic will probably involve showing ownership of those nodes, nullifying them, etc., etc. And ultimately, what gets out of the user machine is a zero-knowledge proof of correct execution with a bunch of commitments and a bunch of nullifiers. And that's it. And optionally a bunch of public function calls to be executed on the sequencer side on the node. So when the transaction gets included, first of all, the zero-knowledge proof is verified to make sure that the user is not lying, and the public functions are actually executed, and those effects are actually added to world state on the chain. I think that's most
amazing.
Sorry, L1. Yes, we're a roll-up at the end of the day, so all of this gets rolled up and sent to L1 eventually.
Yeah, how long does it take to make such a transaction? Because it's way more complex than a normal
Yes. I think we're in the order of 12 seconds, Josh. Something like that, give or take. So, of course, the most expensive thing is proof generation, by far. Like private execution is pretty fast, and like the private local database of the user is not that big. Like, remember, we are just going through the user's nodes, it's not the entire world's nodes. So all that part is relatively fast, and the proving system is optimized for a lot of recursion. So, folding technically, but recursion, so that you can have multiple function calls involved in your transaction, and you don't need to pay a big overhead for that. And it's also optimized for low memory consumption, so you can run in a mobile phone without issues. I think the last tests were around the 10, 12 seconds and 300 megs of RAM. So we strive to keep the memory usage under 1 gigabyte to make sure that proofs can be safely generated on the browser. And I think we're fine.
I think that 10-second proving time was for a transaction that was doing a swap on an AMM. So it was interacting with 2 token contracts and an AMM contract. So just a simple token transfer will be faster.
Yeah.
Like your transaction times are highly dependent on what's actually going into the transaction. One of the wallet teams yesterday was doing a demo at the ecosystem dinner, and they got it proving natively on a mobile device, and I think a simple token transfer on a phone was like 10 seconds just for a token transfer, which is pretty good. And then if you're on your laptop or desktop, it's going to be much faster. Just have a lot more resources.
So you were mentioning all these trees. Do I have to manually update all of that?
That's such a good question. Luckily, no. Even as a developer, you don't really have to handle that. So creating the nullifiers and the commitments is handled in the note itself. So I was saying there's some methods associated with the note as well as the structs. Those methods do create those nullifiers and commitments. And we have created some notes for you guys. And also there's like templates and things like that to be able to basically just easily create notes, to create your own notes with whatever data you want inside there. And then in terms of like actually adding it to the Merkle trees, so smart contracts on Aztec are not written in Solidity because obviously you have to be able to handle all of this complexity. So instead they're written in Noir. And we have created, well, the Aztec team have created Aztec Noir, which is basically wrappers around Noir syntax that makes it so that you don't have to touch any of that. You don't have to handle any of the adding to the Merkle tree or like any of these things because Aztec Noir does all of it for you. That's kind of the point of it. It's just a framework that handles all of these complexities, yeah.
Like if you look at the token contract in Aztec, you define a mapping from addresses to balances, to a set of nodes that represent balances. So you get pretty much the same abstractions that you are used to when working with regular smart contracts. And the library, this library, think of it like operating system calls, like handles for you all this manipulation of nodes and nullifiers and whatnot. If you want to go low level and do it yourself, please by all means. But yes, we have this higher level library so to make your life easier.
So with the public state change proofs, that makes sense to me. But with the private ones, if only the hash goes on chain, what prevents me from generating, a state change that I'm sending 1,000 tokens to you and then double spending privately? If it's only the hash on chain, I don't see what prevents you from generating valid state changes.
Do you want to take it one?
No, you can go for it.
Okay. The nullifier tree. The one condition for the global state to be valid is that you cannot emit the same nullifier twice. Like the nullifier tree guarantees that every nullifier is only present once.
So one UTXO is going to generate the same nullifier?
Yes, that's the key. Nullifiers are deterministic given a node. Sorry? The address, basically out of your, let's say your private key, if you will, you derive a secret that's deterministically derived from your private key and gets mixed into the node to generate the nullifier in a deterministic and secret way.
If I can, follow up on the question of who maintains the Merkle trees.
Yes.
So if my goal is to use nullifier to hide the consumed UTXOs that I want to spend, I need to generate the Merkle proof based on the Merkle tree, and then that feeds into the circuit to generate ZKP for inclusion. So I'm not going to give the UTXOs I want to spend to some other party to generate that, right? So the best way is for myself to generate the Merkle proof and then ZKP. Is that right?
Yes.
So as a result, if I'm using a mobile client, then I better have the Merkle tree inside the client.
Yes. Right now, you depend on having access to an Aztec node that has the trees and can serve you with the proofs. Sorry, with the Merkle proofs. Because otherwise, you're like that node that you're querying for the Merkle proofs can link and can associate what nodes you work with because they see the kind of queries you make? Yes, that's a very good question. And yes, we assume that we have a node that you trust that is not going to leak your privacy in that way. Could be a node running at your home, could be a provider you trust in that, or if you're on your machine, could be something running on your machine. In your laptop, in your mobile phone, it's impractical to have the complete set of Merkle trees. Something you can do, however, is you can store like existing Merkle paths, and like whenever you need to, like you keep them and you just prove against an old world state. That also works. That's also an option. But yes, it's a leak, and it's something that we're working on, so you don't need to have your own node. Yes.
Okay. Thank you.
Very good question, by the way.
Hi. So about how long then for a transaction in a sequencer, received from a sequencer, to be processed for one block only at the blockchain, and how long does it take to be eventually finalized? Just want to get a feel of the UX.
That's in flux. Today, it's 72 seconds for going on chain, for going to L1. We commit state every 72 seconds, every 6 L1 blocks. That may change in the future, not that much. And proving happens every 32 times 72 seconds. Can someone help me on that? It's 32 times 72. That's in seconds, converted to minutes. That's how often state gets finalized. And by finalized, I mean someone puts a validity snark, a validity proof on chain of correct execution, and that's whenever you can exit from L2 to L1 because you have convinced L1 that the transactions were valid. That's like the best finalization you can get from an L2 perspective. Then you can also wait for the block in which the L1 proof was included to be finalized as well if you want even more assurances. Okay. Anyone did the math? 35 minutes? Okay, that kind of checks out. Yeah, every half an hour you can exit L2 to L1 because an SDK proof validity proof is expected to land.
And if I have a use case that I want the same account to be used on the mobile and browser, that would depend on the wallet implementator on how to sync the private state, right?
Yes, basically, because like you don't want like both wallets to be consuming the same node at the same time. Otherwise, you'll have two transactions going on the chain with the same nullifier, so one of them is going to invalidate the other.
Josh, you mentioned a swap happening between two assets. In that situation, is the wallet handling, basically it's like bundling a bunch of these operations. Are we like recursively building proofs on proofs within each kind of like project's code?
It's one transaction, and private functions in one contract can call private functions in another contract, can call private functions in another contract. So like we have full smart contract composability. Basically, I'm not exactly sure how the contract's written where like, I mean, you call the AMM and then it's gonna call the token contracts. But yeah, there's essentially recursive proving happening. So it's not like bundled transactions, it's one transaction that's just calling multiple functions on multiple contracts.
This is a good exercise.
I was going to say, Savio, you're getting your steps in.
Just a question on the transaction lifecycle. Can you explain a bit more how the other side of the equation works? So when I receive something, how do I know it's mine? Are you indexing all the nullifiers and like brute forcing to figure out what belongs to you? And what component actually does that in this architecture?
Beautiful question. Aztec Connect used to work like that. Like you were expected to brute force the entire chain and like use trial decryption to figure out what nodes were meant for you. We're not using that here, fortunately. There are two options. One option is off-chain delivery of the node, as Ciara was mentioning, which is the most efficient one in a way because you're not paying for blob space on L1 ultimately to actually store that. Still, sometimes you need to actually prove that you have sent the node to your counterparty. Like, let's go, there are two very, very clear examples on this. Like, let's say I want to buy a coffee from her. So I would send her like a note for, how much are you charging me for a coffee nowadays?
Oh, like $100.
$100 must be very good coffee. Okay, I send her the $100 notes.
Thanks so much.
And like, I show her, like, I send them via WhatsApp, QR, whatever, the note. If I don't send her the note, but I have sent the transaction, what happens is, okay, I have lost the note because I have consumed it. She cannot use it because she doesn't actually have that note. She only sees a commitment that's completely opaque to her on chain. But she's not giving me my bloody coffee because she didn't get her money. So I'm sort of incentivized to give her the pre-image to the note, like the note with the $100. Let's go for another example. Let's say we're in a trade, like I'm interacting with a DEX, as Josh was saying. And I'm actually taking an order for, I don't know, DAI to ETH or whatever, or well, their respective assets in Aztec. So I could fill that order privately. I can get back whatever tokens were stored there for the trade. But then I never send the note to the guy who actually put up the order. And I'm running away with my side of the trade and griefing the other guy. So that contract, when you code it as a developer, that needs to guarantee that the other person actually gets the notes. And in that case, you need to make sure that that note goes on chain and is discoverable, which goes into your question, like how the hell does the recipient find that? We have a tagging scheme, basically, where the Pixie can issue queries to the node saying, hey, I want to find out about notes, about encrypted notes that look like this, and they refer to a prefix in the node. And the node, whenever the node syncs from L1, they sync the state of the chain, they also sync these encrypted logs and index them based on these prefixes. These prefixes are not like the address of the recipient, because otherwise you would have linkability, you would understand that there were two different transactions sent to the same person. So to any external observer, those tags are not related at all. But the Pixie, the user wallet, knows how to derive, okay, these are the prefixes I'm interested in. You issue that query to the node, and the node replies back with the previously indexed data, which is the data that the user wallet needs to decrypt to actually form their nodes. So to sum up, sorry, I went in a massive tangent here. The thing is, this is really fun, actually. We spent years building this.
Knew you'd enjoy it.
I love this, yeah. So bottom line, what you get is there are encrypted logs emitted as part of transactions. Those encrypted logs have, think of like an index topic as you have in Solidity. Each node is going to have a completely different index key. Nodes will index that. And the user wallet every now and then will tell the node, hey, give me everything you have for these 100 key values. These 100 keys. And the node will return that data back to the Pixie. The Pixie, when I say Pixie, it's actually user wallet. And the user wallet will decrypt them and store them in their local database.
Okay, so on the latter is like a filtering mechanism. On the former one, this off-chain communication you're doing, yes. Are you pinning any of that on-chain? Is it related to what you're doing on the node, or it's completely separate to what you're doing?
No, on the off-chain case, it's completely off-chain, so you don't have to pay anything.
So it can happen at any time, and on the user's wallet, they need to be able to coordinate on-chain to off-chain mechanisms.
Yes. So that's going to be very application-specific, because it depends, like, is it a payment application? Is it, I don't know, a ticket to a venue? It's like, and how you actually receive that data, that private data, it's going to depend on the application or how the wallet wants to orchestrate that. What the recipient is expected to do, though, is whenever they receive that note, that data, they need to check that there is a commitment for it on the global state. Otherwise, they are given something that whenever they want to use, they won't be able to prove that it's a valid note that they own. So it's on the recipient to check that the note they got actually corresponds to a valid note that was created and is committed to in the node hash tree. Sure.
Any other questions? No. See the time.
Okay.
Oh, there's a question.
I love how dynamic this is. I love how dynamic this is.
Yeah, it's
We're getting
great.
very good questions.
Yeah, we are.
So what's the actual state of the wallets?
Good question. There's currently two main wallets who are building on Aztec at the moment, and that is Asgard and Obsidian. They are here at Devconnect, so you should go speak to them. I actually am not too sure on the difference between the two. Maybe Pally, Josh, do you know too much? I think Asgard is like a browser extension wallet, and then Obsidian is an embedded wallet. Yes, I got that correct. Come on. But yeah, they're the main two building at the moment.
But is it?
Oh, that's a good point.
Okay. Okay. And is it like doable or possible? Because I'm trying it. I'm still like failing, but basically to connect like Privy with Aztec.js, because like I don't know, these two wallets are still very experimental, and why not have a third experimental wallet?
Is Privy just like a normal EOA wallet?
Yes, and they support all EVMs, they support Bitcoin, Solana, but they support just signing basically everything. And there is like a SSH example from Aztec in this Aztec package. And in theory it should work, but I still didn't figure it out 100%.
Yeah, you're not going to be able to use Ethereum wallets just like with Aztec, because we have these additional keys, like the nullifier key. There's public keys associated with accounts, so you can encrypt notes to recipients. You could create, we have account abstraction on Aztec, so you can create Aztec accounts that are controlled by ECDSA keys.
Exactly, this is my approach. Yeah.
But there's additional keys that are required to make Aztec work. So like wallets in theory could have, I think they could make deterministic generation of the additional keys from those ECDSA keys, but I'm not totally sure about the cryptographic security of that because I'm not a cryptographer. But like for Aztec Connect, we did generate Aztec Connect keys from signatures with MetaMask accounts, which was cryptographically secure. So I think it would be possible to build something, but I'm not exactly sure how it would work.
With MetaMask Snap or just like real? Oh.
It was literally just a signature. Like a MetaMask would pop up, have you sign something, and then the randomness in the signature is sufficient to actually use as a private key.
Okay.
In Aztec Connect, which was our previous.
Aztec Connect.
This was our previous product that's no longer running.
Still, like the same approach would still work if I want to build my own, like on top of Preview or MetaMask. It should still work, right? Like, amazing.
Like, to be clear, like
maybe
you would generate your private key out of like a private key for your Aztec account from MetaMask or whatever it is, but then you need a full-blown Aztec wallet to actually run the thing, because you need something that can execute code and can generate proofs, and MetaMask cannot do that.
Yeah, MetaMask cannot do this. Okay, thank you.
So.
Yeah. Is it possible to connect in some sense like Aztec and Zcash? So, for example.
Yes, and that is exactly what Harsh has worked on. He created a project connecting Zcash and Aztec. Maybe, Josh, can you give a little bit more context on what you did?
I don't know the details. Harsh is literally giving a talk at the same time in the other room, so he's around. So like if you just step out and find Harsh, he's wearing a Noir lab coat. So
he also made a video. Sorry. He also made a video on it, I think. Did he make a video? No, an article. I think he did a video on something else, but he did an article on what he did with Zcash as well. But yes, you can definitely connect it. We've done it. So you should look into that for sure. I am not sure on the details with that. It will be, because Zcash is an L1, right? Yeah? Yeah, it'll be with the portal contracts then, I assume he was messing around with.
Possible.
Maybe he deployed the portal contracts onto Zcash?
Better check with Harsh.
Check with Harsh, yeah. I'm guessing there.
Yeah, it's doable. Like, you have full programmability in an Aztec smart contract. So yeah, you could totally build something that verifies state from Zcash and consumes it. Yeah.
If you're familiar with how like the near intense bridge works between Zcash and near, Harsh leveraged the same type of architecture, but instead of near being the other side of Zcash, you did use Aztec. So instead of like, I mean, when you're using near is a public blockchain, half of your trade is public. If you do Aztec as the other half, you get full privacy.
Anyone else got any questions? Otherwise, we can pass on to Josh, if he's ready. So thank you, Oh, we've got one more question.
Another one. Go.
What version we should use of Aztec package? Because there is like next from the branches, there is like 3.0.0 Devnet 5, which, but the deployed version is the Devnet 2. If you connect to RPC, but there is also the testnet, there is also edition. And what should I pick as a developer? I was going for the DevNet 5, but I'm not sure.
And you also, there are 3 more networks that you also don't know about. Yes.
Yeah.
Oh, tell me more.
I'm going to talk about versioning because I'm in mind, but yeah, use DevNet. But I'll talk about the difference between the versions and which ones to use.
Okay. In his talk in a second.
Couple minutes.
Yeah. He'll be doing it. He'll be doing a run through of what to install. So he'll go through all the different versions and which one you should use.
In this room.
Yeah.
So
literally in a second.
What I'm going to do, I'm going to jump up here and I'm going to basically show you guys what software you need to get started. We're going to run through, the nuances between versioning because that's like one of the first hangups people run into.
Sorry.
And then we'll start the sandbox and run some scripts and talk about exactly what's happening. We're trying to like make some of this stuff more real, looking at code and running scripts, and then give you guys resources to actually, walk away and know what to do to start playing with Aztec. Yeah. So that's what's next.
I think we had other questions, right?
Perfect.
Yeah. Assuming we have time. Okay.
Thank you. Hopefully the last question. The encrypted node, maybe 2 questions. Do I have the option of not sending the encrypted node to the chain, but just keep it off chain? That's number 1. Number 2 is, for the encryption scheme, have you guys thought about post-quantum security schemes, and when is that coming? Thank you.
Very good questions. On post-quantum, I'll have you speak with Mike from our team. He's been the one researching that. On the first question, that's up to the application, basically the smart contract developer. Like at some point when you're writing your smart contract, like you're writing the code for the token transfer, you'll have an option for saying, okay, I want to send a node to this other guy, and you can either enforce it or leave it up to the wallet developer. Sorry, leave it up to the wallet, and then the wallet decides either by itself or on behalf of the user, what the user wants to do. This basically relates to some code being constrained or not within the circuit we're writing. So you can leave, like the fact that the node was emitted, you can leave that unconstrained. So the end user can generate a zero knowledge proof of validity, regardless of whether they took that code path or not.
Thank you.
For quantum security, since we're just storing commitments on chain is the only required, you don't have to encrypt a node and put it on chain. Commitments are quantum secure. You can't like go figure out what information goes into a commitment with a quantum computer, right? No. So when we talk to application developers about how to design applications, I'm even reluctant to suggest people put highly sensitive information encrypted on chain at all. Like token balances, like that may be decrypted in 5 years, less sensitive, but like if people are talking about putting medical records on chain and be doing stuff there, I'm like, maybe don't do that, or like just do it all off chain. Don't put them on chain, just keep the commitments and you can still do compute on them and use them in your application. So.
Quick question about what you mentioned before. If you do private function, calling a private function in another smart contract, is that recursive proving or not necessarily? That is recursive.
It's folding, but yes.
Okay, so it has good performance.
Sorry?
Good performance.
Very good. Yes.
Cool.
that's all the questions, and we'll pass over to Josh. If you think of anything else, you can probably ask at the end. But thank you all, everyone, so much.
Thank you.